Okay, great. So hello, my name is Vishnu. I'm a postdoc in Nick Jackson's group. We're in the Theory Center, and today I'm going to be talking about our efforts to model organic semiconductor doping uh, in using Reactive Monte Carlo. So the systems we're interested in are organic semiconductors. Here are some very classic examples of organic semiconductors. They're basically semiconductor material made out of either organic molecules or organic polymers. A common feature of these materials is they have these ring-like structures with conjugated double bonds. And the way electronic transport works in the systems is because of the conjugated rings, you have good charge delocalization within a molecule, uh, but there's weak bonding between molecules, van der Waals. So there's charge transfer difficulties intermolecular, making them better than polymers that don't have these type of conjugated motifs, but still not a conductor. And these are quite useful systems. They're not very new. They've been around for several decades, I think since 50s or 60s. In fact, their applications have been out there since the 70s. The Xerox, in fact, no, the IBM photocopier, the first photocopier that they released in 1970 used an organic semiconductor for the photoconduction part in the drum. So it's been applied since then. And the main advantages of organic semiconductors is you can solution process these systems. You don't have to have the very high temperature nanofab facilities that say you would need for silicon. You can use spin coating or inkjet printing. This can be done at room temperature in a fairly cost-effective manner. You can deposit on plastic substrates instead of depositing on glass. And by depositing on plastic substrate, you can make flexible electronics, which we're already seeing examples of those in what the hot area is mobile phones. So you can see the flip phones and the foldable phones, which are happening right now. I mean, they'll probably fully take off when Apple releases one, but there's still there. That's right now a big application. But OLEDs have been applied for several years now. OLED displays are used in almost all type of consumer electronics and can offer much better quality than an LCD display. And they're incredibly cheap compared to regular semiconductors, especially when it comes to things like sensors or TFTs and things like photo conducting devices. So again, OLEDs and semiconductor and solar cells. However, unlike silicon or conventional semiconductors, these are very low mobilities because of the aforementioned weak bonding between the different molecules. You have van der Waals. So charge is quite localized on each of the molecules. And you have, instead of having a bunch of charges that flow through your system, you have sort of charge hopping. So you have electrons that hop from one molecule to another. And I have here a comparison of some of the mobilities for different systems that I asked ChatGPT. And you can see that the mobilities for amorphous organic semiconductors and even crystalline organic semiconductors are much worse than inorganic systems. And they also have significant lattice vibrations compared to regular semiconductors, which can often make things worse. So you need to dope, of course. That's true for inorganics as well. But here, doping is also much trickier. Here, I have a classic example of a p-type dopant, F4TCNQ, shown here on top. And I have a classic organic semiconductor, which is P3H3, polyhexyl thiophene. And this has this type of integer charge transfer doping reaction here, where you have an electron that goes from the P3H3 to the F4TCNQ, leaving a hole at the P3H3. And while this type of doping is fairly successful, you need a very large amount of doping in these type of systems for it to be effective compared to inorganic. So here in silicon, for example, at the very extreme, you need one dopant per 100,000 silicon, and that's at the degenerate level. For conservative doping, you need much less. But for amorphous organic semiconductors, you can need up to almost 10% doping, which at that point I don't even know you can call that doping. It's almost like an alloy. So if you have 10% doping, that has serious morphological implications because the doping will now affect uh, the actual crystal structure or the RDF of your system. So all those very neat theoretical diagrams that you may have seen for silicon, where you can just take out one atom and then take out a silicon atom and then uh, put a phosphorus atom there, and then you'd add one energy level to your band gap, and you assume your rest of your morphology doesn't change as much. Those type of things don't apply anymore. So your morphology and your doping are very coupled problems. So here are the four areas of study I think are very useful for computational modeling of organic semiconductors, uh, for which I'm currently going to talk about the first two. So first is study the doping efficiency, which is once you dope your system, how many of your dopants are actually useful, as in how many of them are actually ionizing. And that can be very easily sort of quantified by taking the amount of F14Q ions that you have, dividing by total amount of F14Q. Second is the effect of doping on the morphology, and then as a result, the effect of the morphology on the doping. Since these are coupled, will cyclically affect each other, and capturing that effect is important. The third thing is the fate of the holes produced. So once you dope and you have all these extra carriers, are those carriers actually useful? Like how many of them are actually producing free carriers that will lead to conductivity, or how many of them are getting trapped in one of the many trap states that can be present in the system? And then finally, some sort of first principles or pseudo first principles calculation of carrier mobility and conductivity in these systems, which is sort of the final goal of all of this modeling. So to that end, what we're looking at is the atomistic reactive Monte Carlo molecular dynamics approach. This is the only approach uh, that exists that we can model both the doping reaction and the morphology. So using MD, of course, you can do very large scale morphology analysis. And using first principles calculation, you can study charge transfer and doping. But those two exist at very different scales. I mean, MD can be done for very large systems, but it doesn't give you anything about charge. Uh, First principles, very good at charge, but you can't do more than a few hundred atoms. So here we have a method that tries to combine both of those things, where it uses MD uh, to look at the morphology, but we use a reactive Monte Carlo move to model the doping. So it's fairly straightforward. You randomly take an OSC molecule, dopant molecule, and you switch them out for a charged OSC molecule and a charged dopant molecule, where the atomic charges for each of the neutral and charged states are obtained from DFT calculations. And you cycle between these MD steps and Monte Carlo steps till you reach equilibrium. And the way you would do the MC was using this metropolis type condition given over here. It can be quite straightforwardly derived from a semi-grand canonical ensemble. So to give you a short overview, so you would have some sort of an MD box that has been at the density that you require. And you would alternate between, say, running NVT MD at 300 Kelvin for a given amount of time. And then after that, you switch to Monte Carlo, where you pick, say, a charged state, so either neutral or charged. And then depending on that state, you randomly choose a semiconductor molecule and a dopant molecule. You switch out your charges quite straightforwardly. You calculate energy changes at this point, and then accept, reject, and then you do a bunch of MC steps, and then you go back to MD. So that's quite straightforwardly our approach. And we've implemented this approach as a fix in labs. It is available publicly on our group GitHub page. And it's a fix that has to be run with some other MD fix, of course, like NVT. And you can specify the number of NVT steps. So here I've specified 1,000, this 1 picosecond of MD. And then after every 1 picosecond of MD, I do 200 MC steps. And then a bunch of parameters for the size of my system, the number of molecules, temperature, and so on. So now I'm going to show you some basic tests that we've done using our implementation. So first thing is a sanity check, of course. Let's say you have an equal concentration of P3H3 and F4TCnQ, your OSC and dopant. What happens if you set your dielectric constant at the extreme limits? So if your dielectric constant is extremely large, then there's basically no effect of charge in your system. You have basically a bunch of neutral point particles, and your entire doping efficiency is going to be controlled by your delta G of the reaction. So if your delta G is zero, then there's truly nothing governing the reaction at all. So you have 50% doping efficiency. It's basically a coin flip. And if you start biasing the reaction with positive delta G, that means you don't want it to happen. So your doping efficiency will fall off. And then as you start encouraging it with negative delta G, your doping efficiency will go up. If you go to the other end, where your dielectric constant is really small, that means your electrostatics dominates, and nothing you do with the reaction barrier itself matters. So your doping efficiency reflects that. It's pretty much a straight line over delta G. So this is a basic test case. It's sort of a sanity check to ensure that we haven't gone completely wrong in our implementation. So now we can get to an actual system, which is P3H3 F4TCnQ at about 20% doping and at the experimentally known density, which is about, I think, 1 to 1.1 gram per centimeter cube. And here we see it goes from fully doped to not doped at all, from over 1.3 to 2.3 EV. That's an encouraging charge transfer energy range, which has been observed previously as well in a first principle study. And a spectroscopy study of P3HT, they found peaks at about 1.3 EV and 1.6 EV for integer charge transfer. So that's an encouraging sign that we're seeing something that qualitatively makes sense. And at those delta Gs, you see a very high doping efficiency, about 80 to 90%, which is also something that's qualitatively known to be true. Doping efficiencies of up to 80% have been observed in experimental studies of these systems as well. Did you have a question? Ah, ah, hmm. And we can also look at the RDF, which is sort of the selling point of this whole approach, is that you can look at the doping charges and you can also look at morphology. So you can look at morphology before and after. And the before is basically what happens at the very high delta G where nothing doped, and what happens at the very low delta G where everything doped. And the most striking difference is you can see in the red line, which is the OSC dopant RDF. You can see that once it's doped, the OSC dopant RDF has a very pronounced peak at a very small distance, which makes sense because now your dopants are charged with negative charge overall, -1, and your OSCs have a positive charge. So the electrostatics will want those two to interact, and it will not want the like ones to interact. So that explains that peak. So again, that's very intuitive result that shows that we're seeing something that's qualitatively sensible. As for quantitative comparisons with experiment, that will require more further parameterization of the charges themselves and the delta Gs, which is something we're working on. Now, the interesting thing about these systems as well, apart from the integer charge transfer, is that they show something called a charge transfer complex, which is instead of having just one charge going from OSC to dopant, you can have them interact to create a bunch of states, effectively resulting in sort of a partial charge transfer. And we can model that interaction as well. So instead of having 0 and 1, we can have intermediate states and have Monte Carlo steps that jump between intermediate states. And accordingly, our acceptance criteria will change in that way. And we can then do a doping efficiency calculation, looking at how the doping efficiency changes for different charge transfer states. And you can see that it's still majority +1 -1, which is what you see experimentally as well, with trace amounts at +0.8 -0.8, and so on. And your RDF is also very expected because at the end of the day, everything dopes. and you have very strong peak for the opposite type of species. I'm going to skip this part, and I'm going to show something that we're working on, which is kind of exciting. Is in the original box, all the dopants are quite dispersed. But what happens if they're aggregated with something that's been seen in experiment? And it's a study that you cannot do at scale with any other method. How the doping will actually change if you have this type of system versus that type of system. And that's something that can be done in our method. So we started with this system and ran our RMCMD method. And you can see that the doping efficiency falls off a cliff, which is quite expected because you have a bunch of these dopants together. And if you have a bunch of negative charges together, that's quite bad energetically from an electrostatics point of view. So the system will not want that. So far fewer of them actually will ionize. So that's quite a neat effect to have. And then you can also see that once they're doped, they'll no longer actually want to be aggregated anymore. So you can see that if you start with something that's aggregated, and then you do 4 nanoseconds of RMCMD, where roughly half are doped, you can see that now they're trying to move away from each other, and they're no longer in that compact aggregated way. So that's an interesting effect that you can get from our method. That's novel. So to summarize, we've introduced an atomistic reactive Monte Carlo method that can study doped organic semiconductors at actually meaningful scales classically, and it has been implemented as a fix in LAMPS. It's available in GitHub. I've currently submitted it to the main LAMPS repository. It's going through some review by LAMPS developers, but in like a month or so, it should probably be a part of the main LAMPS repository and can be downloaded from there itself. It can deal with both integer charge and charge transfer complex with partial charges as well. You can also look at conformational effects, such as aggregation. And we've tested it on P3HT with FOTCNQ, and it yields sort of qualitatively sensible results. Now, there's a lot of future work. First of all, we want to see quantitative Bayesian experiment. That's, of course, the most satisfying thing when things match. You don't have to spend time justifying to people why you're correct. You can just show a nice result showing that they match. So that's something we're working on because we have a lot of parameters in our system in that your individual atoms have charges that have been got from DFT, and then we have to ensure that those are tuned correctly. We have a barrier that has to be tuned correctly. We have to start from a system that's actually experimentally, maybe we start from an experimental RDF and start with doping concentrations for which there's exact experimental data. So those things are ongoing. And we're testing the effects of aggregation. I showed you some results. We also have explicit solvent molecules in our system. So we're putting a bunch of chlorobenzene solvent and we're studying how that affects the doping as well. Also something you cannot do in existing methods. We can also look at how the polarity of the solvent affects things. So if you prepare your system in chlorobenzene, which is not super polar, versus you prepare something with an acetonitrile, which is much more polar, how does that affect the doping? I think it should significantly because if it's more polar, it will mess with the electrostatics of your system and it will discourage doping. Regiorandom, which is regioregular, which is how the side chains affect your system, because the side chains are kind of annoying. They don't really do anything for in terms of the physics of the system. They're there for solubility and things like that. But how do those things affect your doping? And we have a bunch of other effects also that we want to test. So basically, yeah, we're currently in the stage where we have this tool and we're trying to apply it to various systems and see what interesting results we can get. Yeah, that's basically that.
And if there's any questions, I think we have time for one question.
You talked about the sanity check, and you mentioned that for your sanity check experiment, you were doing equimolar dopant to polymer.
Yeah.
Are you referring to repeat unit or are you referring to polymer chain?
Uh, So one polymer molecule in our is an 8-mer of polymer. Yeah.
Okay, right.
Yeah, so we have in that system, there were like 100 8-mers
Okay.
and 100 dopants.
Thank you.
Mm.